All right, so implicit it just has to do with functions that are defined in more than one variable. So let's kind of define that first. And this is kind of an interesting process, I think. So explicit equations would be like something where it's just one. Let's say x squared minus 2x plus 5. So there's just one variable, and then we have f of that variable. Implicit is functions like for circles. So if we had like x squared plus y squared is 16. So now it's not one variable isolated, but we're dealing with two or more. So not all of these explicits are functions. How do we know something's a function? Do you guys remember that definition? Yeah. For every input, we get one output. And then I think you were going to talk about what?
Vertical line.
Yeah, the vertical line test. So,
How does that work? Like, if there's like a vertical asymptote, or if there's a pole or something like that, is that because technically there's no output, or would the output just be like this one exists?
right.
So that would be it.
Yes, it's still
Okay.
a function. Yep.
Okay, that makes
So
sense.
we run into the issue if we put in, like, think of a circle, of course, like this one. Do you guys remember what the equation of a circle? Did you do circles and ellipses in pre-calc?
Yes.
Okay.
And the cardioid.
So
Oh yeah, we did.
What did we?
Yeah, we did.
this is the radius squared for the circle.
Yeah.
So the radius would be 4. And so if we plug in, let's say 2, our vertical line test would fail because we have 2 outputs. That's the an asymptote is okay, but not that. Anyway, so how do we take the derivative of something like this when we have more than one variable? So what I want you to write somewhere on your paper is this phrase, with respect to, we've used that, with respect to is a huge concept with these. So what are you differentiating with respect to? In other words, is this an x differentiable or an x derivative, y derivative? If we were doing like a volume formula, let's do like volume of a cylinder. So pi r squared h. Well, if we did dv, we could differentiate this function relative to the radius or to the height. So we would need to know, hey, are we differentiating this relative to the height? Well, then that changes how we do this implicit part. Okay? And when we do related rates, we're going to talk about making sure we write it out in implicit differentiation correctly. Okay, so if we look at all these, you notice all of them have a dx. So we're differentiating with respect to x in all of them. Okay? Let's maybe make that note. I wish this word was shorter. Now, I'm not telling you, this is not a note saying that we always do it that way. Just note that these are. Okay, so d dx of x is kind of like thinking of it as dx over dx. This is not a fraction, but it does look like one, and so we know it's just 1. But if we work over here, now we're differentiating some y with respect to x. So the chain rule comes in terms of thinking of this as, well, I have to do the derivative of whatever is here, and then with respect to its own variable. So what's the derivative of y? Yeah. So it's 1. We don't need to write the 1. But then we have to say, okay, but take the derivative of y with respect to x. Okay, we have to account for the fact that this is not an x, I guess we could say. Okay, dx of x squared we know is 2x. And then if we don't ever write this, we haven't, and we won't, but it's really 2x, and then the derivative of that with respect to x. So we know that that's just 2x. Over here, though, now we're doing y with respect to x. So this is 2y dy dx, because we have to note that we are taking that derivative with respect to x. And again, it's not a fraction, but you can think of it as, well, it doesn't simplify down. Okay? How about this one? You guys remember your exponential derivative of e? So we have two things, right? So e to the 5x, and then chain rule says, you might have said it, I just didn't hear, but times 5, right? So differentiate the whole thing, and then differentiate the inside parts, so layers, and then again, it's dx over dx, but really we would just write this as 5e to the 5x. Okay? How about this one?
Would be 5 dy dx e to the 5y.
Yeah. Yep. So you do the derivative of the function part the same way, but you have to stick this dy dx. Or if I had left that volume thing up here, we would have to say dh dt or dh d, whatever we're differentiating with respect to. Or I guess in that case it was dv dt. All right. Any questions on that? Okay. So what we're going to see is functions that have both x's and y's. The x, so notice this one, it says find dy dx. The x derivative, since we're differentiating with respect to x, will be the normal ones that we've been doing for the last whole chapter. And then we'll just have to tack on this dy dx to the other ones, and then algebraically isolate it. So take the derivative. So we're going to say dy, let's do it after. So 2y dy dx for this first term. How about you guys tell me the next term? Well, 15. Okay, and then how about that last one? Yeah. So 3, and then, oh hey, we differentiated with respect to x. So, okay, so that's the derivative, but our goal was to find dy dx. So that's the calculus part. Now we just need to do algebraically get these by itself, get the dy dx by itself. Okay, so we want to collect our terms with the dy and dx on one side. And it says left side, it doesn't have to be, it's just whichever side makes the most sense. So we have 2y dy dx minus 3 dy dx, and then put your 15x squared on the other side. Good on that? Okay. I guess I would probably highlight this because you'll do this a lot. You don't necessarily always do it, but it does come up fairly often. So factor out that dy dx. And then how do we solve for dy dx?
2y.
Yeah. Okay, let's talk about what that means. Just since it's been a little while, what does a derivative mean in general?
It's instantaneous rate of change.
Yes, instantaneous rate of change. So the slope of the tangent line. Okay, so notice this one would be the slope of the tangent line, but now we have two coordinates to plug in. Okay, so if we go back to this equation, this is, because it has a cube, this is some version, but let's pretend for a moment that it was a circle. So if I said an x coordinate, let's say I put something in here, say I pick -1. Well, we're going to have a tangent line there, but also a tangent line there. Okay, so we'll do a problem like that in a minute, but we'll have to plug in order to, if we wanted to find the slope, we'd have to plug in an x and a y of both of those points, since these are implicitly defined functions. So let's try these. Do you want to do this first one and just check? How about that?
Yeah.
Since it's kind of like the one we just did. How'd that go? Got it? Okay. All right, this one you have to be a little bit careful because we have a function inside of a function. So what rule do we need to use? Chain. So what's the derivative of sine? I just said it. So cosine. Okay. And then times. Now we have two things going on. Yeah, product rule. Good. Okay. So product rule, remember v du plus u dv dx, but in this case we have a y. So what do? Y, right? Y times the derivative of x, which is just 1, plus the derivative of x and then dy dx. I said the derivative of x, but I meant the derivative of xy with respect to x. Okay? And then on the other side, just 10. Good? Good? Okay. All right. So now we work to get that by itself. So what is 1 over the cosine? Yeah. Yeah, so we could say 10 secant xy. It just kind of looks nicer. Okay, and then subtract y and divide by x. So just keeping an eye on product, like chain rule, product rule, all those things. And anytime, I wish this would say that you might add this direction, but find dy dx. What if it said find dx dy? Could we do that?
Yeah.
What would change? Like what would this be? Let's just do the first line of this if it was dx dy. Yeah, so it'd be 3y squared minus 2 dx dy equals 4x cubed dx dy plus 2. Okay, so it changes it, right? So that's why we wrote that note about really pay attention to what you're taking the derivative with respect to. All right, so this is kind of what I was mentioning a second ago. Find the equation of all tangent lines. So, of course, we're going to use the point slope form. And we need that slope. So, what are we talking about when we need slope in this case?
You need your points and then or what are you saying?
Well, you're right. We do need our points. But my question was, what are we talking about when we know we need this m value? What is it called in this kind of a problem? It's dy dx, yeah. Yep. Okay.
Would it be square root of x on the square root of x? I mean, square root of 2 on the square root of 2.
For what? For the y coordinates?
Yeah, like. Well, because it's.
I guess I don't know what you're asking.
It's a big unit circle. Can we just?
Well,
Well,
it's not actually a unit circle because the radius is 2.
Yeah. So if it's half. Okay. No, I don't know.
Okay. Let's get our points, then we'll do slope. So how do we get the y? We know the x coordinate is 1. So how do we get the y coordinate? Yeah. Don't forget plus or minus when we square root that because we need both the positive and the negative. So if you want to put those on there, You don't have to, but it's kind of nice. So this is 1 negative root 3 and 1 positive root 3. And then let's do slope. Okay. So 2x plus 2y dy dx equals what? 0. Yeah, be careful there. Since it's just a constant, it doesn't matter what we take the derivative with respect to, right? It's just 0. And get dy dx by itself. So shoot, I messed that up. Do you see where?
Should have a negative good point.
Yeah,
Right there.
that was positive.
Because you're dividing by 2y.
So let's rewrite that. Okay, now what?
No.
Yeah, notice now, this is the same, very similar process to what we've done, but now our slope depends on two things, right? So, slope value needs both x and y. Alright, so let's call it M1. So 0.1. Actually, I'm going to draw that in a second. So, 0.1. Okay, so our slope in this case, we'll use the positive version of the x, or excuse me, of the y. So it's actually a negative slope, which makes sense. It's going to come in like that. Okay, and then M2 is the, let's make that like that. The positive version. Let's see, I'm running out of room. I think I'll just write it over here. So line 1 is y minus root 3, and then our slope, negative 1 over root 3, x minus 1. Everybody good on that? Okay, line 2. Yeah. Okay. So it's a little bit more involved than what we did before, but same process. All right. We're kind of running out of time, so maybe we'll finish that. Did you notice they fixed the bells today a little bit?
Yeah, they're not 2 minutes early.
Yeah. Yeah. Just a quick reminder, I guess we could finish this little box. Horizontal tangent exists when the slope is what? 0. Vertical tangent when the slope is undefined. So divide by 0. So just think about setting something like this equal to 0, or which means the numerator is 0, or making it undefined, which means the denominator is 0. And then we basically do the same process for the rest of it. Okay? So it's just a slope, a quick slope calculation in that. All right, let's do a few of these.
All of them.
All of them. How about do 1 to 13 and do, well, I guess 2 to 12. Do the odd or the even ones.
Wait, 1 through 13?
No, 2 to 12 evens, just the even ones. Yeah.